Very well. It's my pleasure to present in Xiamen University of Technology a topic that probably it is interesting to our students, especially research student, postdoc student, PhD student, and so on. I shared my screen, so probably you can see the first page of my screen. Let me put it in slide mode, just a second. Very well. The topic that I am going to talk about is time optimal control of dynamic system, especially multi-degree of freedom system. And I give you some introduction. What is the optimal control? Why time optimal control is important? And what is the problem with multi-degree of freedom? And what is the solution? I present to you a solution that I called it floating time method. That's something that I invented myself, and I'm going to show you that it is a practical, very interesting method, and it is able to solve not just time optimal control, but also energy optimal, jerk optimal, or any other optimal control related to dynamic system. Very well. Before starting the technical aspects of my talk, I'd like to share with you a few photos from Xiamen University of Technology. I was lucky to be there several times for teaching, for research, for speech, and I am hoping that it happens again during the past 2-3 years because of Corona. No travel was possible. That's why we are presenting this research by video. Anyway, let me skip this part and go to here. I'd like to introduce myself a little bit and then talk about optimal control and then main problem of time optimal control and then floating time method, and probably I can discuss a little about future of this problem. On top right, you see me in my office here at RMIT, and I always put this photo, the picture bottom right, to remember that we are nothing basically in this huge world. Okay, so just remember to turn on your mobile phone after leaving the session. Well, this is my appointment at the moment. I am a professor of mechanical engineering here at RMIT Melbourne, Australia. I'm also honored to be adjunct professor of a few universities. One of them is Waterloo University in Canada, which is the place that 20 plus years ago, I was a postdoc in Waterloo University, one of the best universities in Canada. Also, I am distinguished adjunct professor of XMUT, and it is very pleasure. I'm honored to be part of Xiamen University of Technology. Also, maybe you know that there is Ocean University, Xiamen Fuzhou, that I am adjunct professor of that university as well. Fantastic, unique university in the world. Not many universities are doing what this university is doing. Education, I was graduated in nonlinear vibration and applied mathematics. And also my master's was in robotics. And in that master's, I introduced the floating time method. And I worked on that floating time method, the thing that I'm presenting to you today. A few years. And then my bachelor was about internal combustion engine design and so on. I was lucky to do several projects for automotive industries, Nissan, Kia, Audi, Peugeot in different countries. And based on those projects, I gained a lot of industrial experience, mostly related to vehicle dynamics, vehicle stability, chassis design, vibration analysis, and this sort of thing. And since then, I'm working on vehicle control, dynamics, and this sort of thing. Probably you are familiar with my book in vehicle dynamics, which is #1 in the world. That's enough show off. I was lucky to be involved and work with several universities around the world. Here, I listed them, including Xiamen University of Technology, as you can see the list here, some Indian, some Japanese, Chinese, European, Middle Eastern University, and so on. The picture on the left bottom is showing me teaching control in North Dakota State University around 20 years ago or 18 years ago. Well, publication is my ability and my passion. And starting 2006, collaborating with Springer publication. These are the books that I published there. And the top row are those books that I published by myself as single author. In 2023, end of this month, my advanced vibration is coming out, and the rest of them, you can see them. On the bottom, you see those books that I was co-author. The main author was in all of them, Professor Liming Dai, my dearest friend, who introduced me to Xiamen University of Technology. So on the bottom, I am a co-author. On top, I am the only author. Out of these books, these two are very famous because more than 100 universities of the world are using these books as teaching. Because of their importance, they have been translated to several other languages, including Chinese. And here is the Chinese version of these two books. And it's easy to buy it in China. So I recommend you to obtain it. Academic service is a part of academic job. Academic service is what you do for academia all around the world. So majority of important work that I'm doing is to be associate editor of several journals that here you see these journals. And because of that experience, I decided to establish a new journal. That journal, which is called Nonlinear Engineering, I founded in 2012. And for 6 years, I was the editor-in-chief. And then I let it go. And right now it is in publication list. And you can send your research related to nonlinear whatever with application to this journal. Okay, let's go to optimal control, especially time optimal control. And the best example of dynamic system is a robot. Let me remind you that the main job of a robot is pick and place. Pick and place means the hand of the robot. I'm talking about industrial robot, the robot that is working in a factory. 90+% of robots are industrial robots. I'm not talking about research-oriented robots. So pick and place is the main job of robot. And pick and place means the hand of the robot goes at some point, grab something, move on a specified path to a destination and let it go, and comes back to take another one and go, let it go. Pick and place, which is not just grabbing and let it go, it can be welding, for example, is moving the hand rest to rest, means zero velocity to zero velocity. And usually we add zero acceleration, zero jerk at the beginning and end. The path of motion is given and fixed. So the hand must move along that path. So if assuming pick and place is the main job of a robot, when we do it as quick as possible, we increase productivity. We increase the rate of production. So when we introduce a robot, all of a sudden, minimum time control comes to the picture. How can we do this pick and place as quick as possible? Well, we can add a lot of constraints. The main constraint, the first constraint, is that from beginning to the end point, straight line sometimes is not physically possible. There are some obstacles in between, forbidden range. So the path from here to here must go around the obstacle. So somebody must design the path, like an arc, for example. Here in this slide, you see some arcs going around or below the forbidden zone. Design the path is another subject. Let's assume that the path is designed and it is given to us. Now we are supposed to trace the path with minimum time. A robot, here you see 2R robot. 2R because it has 2 revolute motor, 2 revolute joint. One motor is on the ground, as you can see. The other motor, which is here indicated by yellow, is in air, so it is moving. So the first motor is moving everything. The second motor is just moving the second hand. And at the end of the second hand, point P, there is a payload. So this robot is carrying something. Now, how can we control these 2 motors to move the tip point, the payload, on the path that we wish in minimum time? That's the problem. Okay, before going further, let's talk about optimal control, where and when it appeared to the academia. Everything started with brachistochrone. Brachistochrone is defined first by Galileo in 1630 something, and later on Bernoulli in around 1690 something. He introduced. Bernoulli was a member of a family, some brother and father and son, grandson. The whole family were genius and very talented in mathematics. So Bernoulli, I believe it was Johann Bernoulli, who introduced for the first time this problem. Now, what is the problem? The problem says that under gravity, in a vertical plane, there are 2 points, point P1, point P2. From P1 to P2, we have a wire. The shape of wire is not changing, but we shape the wire. And then on the wire, there is a bit. We let the bit go, slides on the wire, reaches point P2, frictionless. And we wish it goes from P1 to P2 in minimum time. Now, the question, what shape of this wire gives us the minimum time? So it is a sort of minimum time path problem. Later on, Bernoulli himself, Johann, solved it. And then Jacob Bernoulli, the other brother, solved it better. And then many people worked on this problem. Solution came from Newton himself. And another solution came from Leibniz, a German scientist. Eventually, the problem moved to Euler. And Euler solved this problem differently. I'm going to talk about that. Differently because all other people were using calculus, something that started with Newton and Leibniz, and then differential equation and so on. But the way that Euler solved this problem was totally different. Let me show you what is the solution on this slide. I'm talking about the right column. The right column says that capital J, I'm sure that you see my cursor. Capital J is integral between T0 to Tf dt. T0 can be 0, starting time. Tf is the final time. And dt is integral of dt means total time of travel. We wish that J be minimized. We call J functional or objective function. On the right here, it shows that dt can be replaced with ds over v. S is the arc of the path, and v is the velocity of the bead. And then, because it is happening frictionless vertical plane, v is the square root of 2gy. Y is the displacement, as you can see the coordinate frame on top left. And then ds from calculus, you remember that it is the square root 1 plus y prime squared dx. When we substitute everything in j, we get this integral. So that integral has integral from point 1 to point 2. A function dx, that function is y over dx. Whenever we get it functional like this, the solution of that, solution means function y equals to f of x. That function that minimizes j comes from Euler equation or Lagrange equation. I'm showing in next slide. Let's assume that we are able to solve j, or solve means minimize j, and find the function. The function would be this equation here. And if we separate x and y with expressing in parametric method, we get these two equations on bottom, which is cycloid. Cycloid is the name of an arc, a curve. How we make cycloid, look at the bottom left. When we have a circle, and that circle is rolling on another curve. Let's say another curve is a flat ground. So the circle is rolling on the ground, any point on the circle or in or out. At the moment, I'm talking about one point on the circle. When it is rolling, that point is tracing in air that shape, which is indicated in red. That curve is cycloid. Any part of that cycloid that connects P1 to P2 is the solution. Okay, this is the solution. As I said, many scientists found the solution correctly using calculus, differential equation, and so on. Cycloid is a very interesting arc, curve, with a lot of industrial application. Here on the left, you see that from point A to point B in several different paths with several different wires, we are releasing some beads. The curve, which is in black, it is cycloid. And as you can see, the black reaches point B the quickest, the fastest, before others. There is one green, which is circle between A and B. It's an arc of circle. That was the guess by Galileo. When Galileo introduced this problem, he tried to solve it, and he found that arc of a circle is the minimum time. At that time, calculus was not invented yet. So Galileo did a lot of experiment. Based on his experiment, he found this is the best solution. Not too far from cycloid, so it was a good guess. Other guesses here, as you can see, parabola, line, or any other shape are not working as good as cycloid. Cycloid is the best solution. There are other applications on the right, and you know better. I skipped the explanation of them to save time. Okay, I said that Euler tried to solve brachistochrone problem differently, and that differently introduced a new knowledge, a new science. Today we call it calculus of variation. Calculus of variation was something that Euler invented to solve brachistochrone. And today we know that calculus of variation is the base for optimal control. Euler assumed that we have a J, functional J, which is expressed by integral of a function totally f, an integrand, f, which is a function of x dot or x prime, and time. Over time, we want to integrate and find j minimized. There are some boundary conditions, means we know the value of x. X is independent variable, okay? And y is dependent variable. So we are looking for y as a function of x. This is the solution of minimization of that functional j. Boundary condition is that we know x at the beginning and at the end. Let me rephrase what I said. In this expression that I showed, t is independent variable, x is dependent variable. So we are looking for x as a function of time. When we replace t by x, x by y, that was my previous expression. I'm sorry. So we are looking for x as a function of time to minimize j. Boundary conditions are given and fixed. Euler said, let's assume that best solution or optimal control solution is given to us, or we found it. Let's assume it is indicated by x star. So x star is a function that minimizes j. Although we don't have it, let's assume we have it. Now let's give a perturbation to x star. Perturbation means adding something very small to x star. So we introduce a new x of a function of time, which is equal to x star plus epsilon something. As you can see here in this line, that epsilon, which is very, very small, guarantees that epsilon times y is totally very small. So x, which is a new guess, is very close to x star. That's called perturbation. When we have something, we add some tiny function to the given function. The total function is called perturbation, and perturbation is a technique. Anyway, he substituted this x of t in the function and then minimized that, or tried to minimize that based on calculating delta j and pushing delta j as a limit to 0 when epsilon goes to 0. Eventually, delta j is going to be expressed as a function, as a polynomial of epsilon. We have epsilon capital V1 plus epsilon squared capital V2 plus higher order of epsilon. Because epsilon was supposed to be assumed to be very, very small, cube of epsilon and other exponent of epsilon are nothing, are very close to 0. We can ignore them. Even V2 can be ignored because epsilon squared is much, much smaller than epsilon. But let's assume that we take two terms. I have something to tell you about that. V1, which is called first variation, is this is expression of V1. And when we apply the minimization of that based on Lagrange method, what we get is this function in the box on the bottom. This equation in the bottom gives us a differential equation to calculate x as a function of time. And this is what we, in dynamic, we use it Lagrange method of deriving the equations of motion. So first variation end up with Lagrange equation, which is a differential equation to solve for x of t. Second variation shows stability of the solution that V1 gives us. To remind you what does that mean, let me go to calculus. When we have a function y equal to f of x, then we find y prime equal to 0, means first derivative equal to 0. That gives us an equation. The equation will be solved, and it gives us x values that at those x values, function y has extreme value. Extreme means it is maximum or minimum. Okay, how do we know that it is for any specific x, which gives us extreme value? is that x as a point of maximum or as a point of minimum? Second derivative, y double prime says that. You remember from calculus that if second derivative at a point is positive, then we call it the curve can hold water. So that positive second derivative means minimum. And if the second derivative is negative, we call it the curve cannot hold water, so it is a maximum. Similar to that, V2 and V1 are working together out of my concern today, out of our scope today, so I skip that. Now let's go and look at this problem in practical way. In practical way, let's assume that we have a mass like a car, like a box on a table. From some point x0, we are moving to xf. So from one point to the other point, we are pushing a force behind that. This force can be positive or can be negative. So it is accelerating or decelerating, okay? And I want to move this box from here to here in minimum time. Let's assume there is no friction, okay? If there is no friction and this force can go to infinity, I can go there in 0 time, right? So whenever we are talking about time optimal control of a dynamic system, there is a constraint. That constraint is that actuation or force is limited. It cannot go to infinity. So there is a boundary for actuating force, for driving force, a maximum and minimum. For the moment, for simplicity, assume that maximum and minimum are equal in absolute. For example, positive 10 Newton, negative 10 Newton, okay? We can change them later. At the moment, let's assume that these are absolutely equal. So when force is in middle, it's 0 force. Now let's get back to that problem. I want to move m from 0.0 to 0.1 meter, for example, in minimum time. The force is limited. There is a saturation for that force. So the solution is that we apply the maximum force up to the middle of the path. At the middle of the path, we decelerate or brake until we stop at the end. Why do we do that? Because the boundary condition is rest to rest. Let's assume that this is boundary condition. So if the boundary condition is rest to rest, maximum force to the middle, switch to the negative, at the end, we are going to stop. That's the solution. The equation is given on the left, which is in the second line, you see F, which is actuation force, is equal to mx double dot minus mu mg. Mu is the friction coefficient, mg, as you know, mass and gravitational acceleration. So if there is a mu mg, then F would be different. At the moment, let's assume that mu, friction, is 0. And this is what we are going to do. And this is the solution. Force is equal to maximum. Let's assume the maximum force is 10 Newton. M is 1 kilogram. We apply the force 10. At the middle means half a meter movement. We switch to the braking and we stop at the end. Now let's assume that friction is existed. It is not 0. If there is friction, friction helps us to stop and prevent to accelerate. It means I have to apply positive F a little bit more and then switch to braking. That switching point is important. The whole problem depends on switching point because we know that at the beginning, we must apply maximum force. At the end, we must apply negative maximum force or braking. Somewhere, we must switch. That switching point is important. If the system, dynamic system, is 1 degree of freedom, switching point can be found analytically. If it is multi-degree of freedom, it cannot be found analytically. So I am going to explain. But before going to multi-degree of freedom, let's see a solution when friction is there, here. The red one is the solution with friction, some value, okay? It has some value. At the moment, I'm explaining the problem. Now, let's assume that we have a multi-degree of freedom, like this shuttle arm. Well, you know that shuttle arm is something similar to the hand of human. It has 7 degrees of freedom. Shoulder, here, shoulder, there are 3 rotational degrees of freedom here. You can try 1, 2, 3. 3 rotation in shoulder, 1 rotation in elbow, and 3 rotations in wrist. Totally, we have 7 degrees of freedom. Well, before going further, let me give you an explanation. 7 degrees of freedom looks strange. Why? Because when we want to locate or move an object, a rigid body, and bring it to a specific location in a specific orientation, we need only 6 degrees of freedom, not 7. 7 means we have 1 extra degree of freedom. Well, why we have 1 extra degree of freedom in our hand? What can we do with that with our hand, or in industry with the extra degree of freedom of a robot? Here we have 7 degrees of freedom. It can go up to infinity. For example, 10 degrees of freedom. What do we do with extra degree of freedom? Is out of the scope at the moment, but you understood what is a multi-degree of freedom system. Usually industrial robot, if they are fully operational, fully actuated, they must have 6 degrees of freedom. And usually 3 degrees of freedom goes to the arm, the main arm, and the other 3 degrees of freedom goes to the wrist. Here you can see a spherical wrist and an spherical arm. So totally you have a spherical robot with 6 degrees of freedom. Here you can see the motion animation for that wrist, which is showing 3 rotational motion for that. And there is another degree of freedom for the gripper to close and open to hold, or that's not degree of freedom of kinematic motion. Okay, now we know what is a multi-degree of freedom system. And I mentioned that switching point is missing. Let me re-express what is the minimum time control of multi-degree of freedom. Imagine a 2R robot that at the beginning I introduced to you, 2 motors. If 2 motors we apply the maximum torque that they can support, then the tip point is not going to move on the path that we design. So there must be a ratio, there must be a proportion, there must be a relationship between these two according to the equations of motion and the position of the end effector, inverse kinematic, and so on. All of them are in robotics. But what is the solution of multi-degree of freedom? I said it is not possible to find the solution analytically. So what can we do? We need numerical method. Okay, how do we know that a numerical method is actually the solution when we gain it? Everything goes to this gentleman, Pontryagin. Pontryagin was a Russian scientist, mathematician. Around 1950, 1960, he and a few other mathematicians worked on optimal control in general, and he mentioned something that when I explain that, you understand that it makes sense. He said, optimal control solution of a multi-degree of freedom system will be achieved when at any instant of time, at least one of the actuator is saturated. So if we are able to find this pattern that at any time, at least one of the actuator, I'm talking about 2R robot at the moment, one of the motors are saturated, means are at maximum or minimum, then we have the solution. Looks very simple, but his theorem, which is proven that this is optimal control solution doesn't say when is the switching point and what is the ratio. These are depends on dynamic system. Now we need a numerical method to find out such a pattern that at any time one actuator to be saturated. When we have that, this is the solution. Now I'm going to introduce a method. The method that I'm going to show you is based on central difference method. What is central difference method? You know, in finite difference, there are multiple methods to discretize a curve, which is the solution of a differential equation. And always we are looking for the value of a slope, means x dot or y prime, doesn't matter. Here I'm showing f of x over x, so I'm talking about f prime. At some point, that point, let's say it is x sub j. At x sub j, I'm looking for a slope. True slope is shown by black. Approximate slope is shown by red. The curve is shown as blue. Forward difference method, which is the first finite difference method, Euler introduced that, and today also we call it Euler method, is like this. At some point xj that we wish to find the slope means arctangent of that line. The slope of that line, we find another point in front of that, x of j plus 1, okay? We find that point on the curve. We connect these 2 points by a line. This line is not the same slope, but if we move xij plus 1 towards xj, that line that connects 2 points gets closer and closer and closer to the slope. At the limit value, it is the same slope that we wish to find it. It works very well. Now you understand that we can define backward difference, means instead of having a point in front, we can have a point in the back. Same scenario. We move it towards the point and we got the slope. Central difference is more interesting. We get 1 point, we forget about the point. We get 1 point in front, 1 point in the back. So we have 2 points, connect them, and then move both of them to the point, and then we get the slope. All of them are working more or less same accuracy, but central difference is a little bit better. There are several other methods that they use, for example, 10 points in advance, 5 points in the back, and there are some algorithm to start the numerical solution out of our scope. Just look at the bottom right. F prime at some point, which is xj, is approximately equal to f, means value of the curve, in front minus the value of in the back, divided by 2 delta x. Delta x is usually constant, and we call it by little h. So that's the central difference equation. Now what I am doing is here. Let's assume that we are plotting x over time, because I'm looking for a solution like x as a function of time, okay? So ti is a point, ti plus 1 is a point in forward, in front, ti minus 1 is a point backward, in the back. I'm connecting these two, using these as central difference. Now, the difference between here and the previous slide is that here, ti plus 1, ti minus 1 are some given value, I plus 1, I minus 1 are assumed to have it, but delta t, which is here indicated by tau I and tau I minus 1, they are variable. They are not constant. They are not little h that we pick at the beginning. I'm going to adjust ti's and find a pattern of these delta t or tau, which I call it floating time. I found the floating time somehow that the addition of them is minimum. Let me explain a little bit more, but before that, you remember even in central difference, when we are, for example, at the beginning of the path, beginning of the time, which here is indicated by T0, we need a point before starting of the dynamic. Means we need an imaginary time, T minus 1. Same scenario at the end. Let's assume that the maneuver is finishing at time Ts plus 1. We need a time Ts plus 2, which is not exist. We are not moving at that time. So these are the problem. There are a lot of solutions. Don't worry. For central difference, there must be some guess or some way to calculate T minus 1 and Ts plus 2. And that's coming from boundary condition. First, if we develop the equation of central difference for first derivative and second derivative by floating time, these are the equations. So these are new equation, central difference, first derivative, second derivative. And as you can see here, the numerator is as we have seen in the previous slide. The bottom, instead of having 2h, we don't have 2 h's. We have 2 time interval, and they are not equal. They are independent, so they are there. And second derivative would be that equation. We use the first equation twice, we get the second equation. Not hard to find. Now, let me explain those imaginary points, how we calculate them, and apply the method to show on simple problem and show you how this method works. Let's get back to the same problem. Mass m, 1 kilogram, is moving from 0 to 1 meter. Maximum force is 10 Newton or negative 10 Newton. And the time, as you can see, axis is here. Now look at the initial condition. The initial condition is rest to rest. Because it is rest to rest, look at the x dot equation. If it is rest to rest, when I'm talking about x0, it says x1 minus x minus 1. In the numerator, we have x1 minus x minus 1. X dot at I must be 0, so these two values must be equal. It means eventually we get x minus 1 equals to x1, just numerically. There is no such a position as x minus 1. Numerically, these two have the same number. Because we are moving from 0 to 1, x0 to x1. In minimum time, the time interval must be the same time interval as the previous one. So we found tau 0 and tau minus 1 equal to each other. Same scenario to the endpoint. So we got the solution for those imaginary points and time interval. Now, look at the equation. The equation of motion is F equals to mx double dot. So far, no friction. And x double dot based on central difference is there. And I'm talking about the first beginning of the maneuver. Now, when we expand the equation, as you can see here, the only variable here is tau 0, because we know x, x0, x1, x2, and so on. So the path is there. The path is given to us, so we know at any point of x where we are. So everything is given on the right-hand side of the first equation. Left-hand side is the actual force. On the right-hand side, we have tau 0 is the only unknown parameter. Now, if I change the value of tau 0, the value of F is changing. So I change the value of tau 0 until F is equal to maximum F. If I make it shorter, this breaks the limit. If I make it wider, it is not using the actuation, maximum actuator. So there is some adjustment. We found the first tau 0. We go to next step. For the next step, we have tau 1. We adjust tau 1 to get F equal to maximum. So we do this and we find all of these floating time until this F is maximum up to 3 points before the endpoint. So endpoint, 1 point before endpoint, and here. Now, at the endpoint, I have opposite algorithm. I know there I have to have negative f. So I have this time. In this point, which is 1 point before endpoint that we must stop here, I have time interval in forward from backward. Time interval before that from forward because it must be maximum. So at that point, the value of f is determined because I don't have any time interval to play with. We substitute these two in the equation and we calculate the value of f. If value of f is breaking the limit, that's not the solution. We are not allowed to break the limit. So what can we do? We get rid of this time interval, we throw that away, we move backward, and here we go one step back, and here from the endpoint, we go one step backward actually, and then we found the time interval to have f equal to negative maximum f. Now, one step before that, we don't have any unknown time. We substitute into equation. We find the value of the f. Sorry. Same scenario. If it breaks the law, breaks the limit, we throw one step away. We move backward until at some point the value of f, which is out of our hand because all time interval is coming from moving forward or moving backward, and f at that point is not breaking the limit. That's the solution because we have found a scenario that at any instant of time, force is saturated, even either positive or negative. I have to show you graphically. Let's assume that these are the these are the statement of the solution. We may have friction. I talk about friction later, but let's get back to what I explained already. Let's assume that here we made the whole x in 20. By computer, we call it 20,000. But here, just to show you, we know that at the beginning, f must be maximum. And at the end, f must be breaking minimum, means negative maximum. Now look at this. We calculate tau. Tau is not shown here. And f is positive to 2 points before the end. We know that end point force must be minus f. So at the point before the end point, I'm talking about the last 3 points. The middle point, I do not have any control on any floating time. The value of f comes from the equation because all floating time are calculated already. One from backward because the last point must have negative f. 1 point from forward because we know that that force must be positive f. So as you can see, this f is breaking the limit. What can we do? We move backward. We throw 1 tau away and we move force from end point to be negative f. And we move backward until we get the solution. And here is the graphical illustration. Still breaking the limit. Breaking the limit. Okay, we are getting better and better. There you go. That's the solution. We found a pattern of f, which is always saturated. That line that connects switching point must be vertical, actually. When we increase the number of increment, that line is going to be vertical. We call this control bang-bang control. Maybe you heard that. It's a funny name, but wherever or whenever we are talking about Time optimal control, bang solution, or bang control means it switches from maximum to minimum at no time. Okay, let's apply such an algorithm to that mass 1 degree of freedom. Moving from one point to the other point, maximum force is 10 and minus 10. When we have no friction means mu equal to 0. Total time would be 0.6019. It's calculated by computer. I'm not saying that this time is physically achievable. Around 0.6, let's say it is second. Horizontal axis is F. So this is in the middle of total time. Total time, when it is switches at 0.3, total time for no friction is 0.6. So when there is no friction, the total motion will finish at 0.6 second, and switching point is around 0.3 second. When we introduce friction, total time will be increased. Friction is a resistance. We have to overcome that friction. So total time of motion will change, switching point will change, and as you can see, 0.2, total time is increasing, and by changing the value of friction up to 0.8, as you can see, total motion is around 1 second, and we are switching around 0.9 second. That's because friction is very heavy here. Okay, here you can see F as a function of X. Now, no friction, exactly in the middle. Middle means 0.5. The total length of motion was 1 meter, or we unified that. By increasing of the friction, as you can see, the switching point physically, what distance is the switching point, will be pushed toward the end. And this is X as a function of time for the motion. No problem. We can put whatever I said in an algorithm, changing one step to adjust F, and then moving forward, and then coming back when we break. All of them is in this algorithm. I don't want to take your time to go into that algorithm. I give you the reference. When we have a numerical method like this, the question comes naturally: is there any guarantee that this method works? So there must be a convergence theorem, convergence test, and it is done. Done means I introduced this theorem somewhere. I proved what is the condition that this method is converging. Let's apply that floating time method to brachistochrone and see what would be the solution of brachistochrone numerically and analytically. This is one problem that analytic solution, exact solution, is given to us. And I'm going to solve this problem again with floating time method and compare these two. Okay? Look at this. First of all, I'm starting from one point, which is 0, 1, and two different points. So two scenarios are being solved. One is from 0, 1 to 1, 0. Here, the blue one. The other one, forget about the first problem. The second problem is from 0, 1 goes to 2 and 0, the black one here. So two different solutions. We know that both solution is cycloid, different cycloid. We apply the analytic solution and we find the solution here. For the first path, t equals to 0.6104084 is the exact solution. Sorry, numerical solution. The exact solution is here, 0.6176. TF1, TF1. This one is analytic solution. The first one is numerical solution. I believe that I had 100 increment. For the second path is this one, goes to B2. The analytic solution is here, 0.8077. And numerical solution is 0.8057. Well, physically, these two are very close, and when we increase the increment, they can be closer and closer. So it means the numerical solution works, at least we have shown here. Okay, now if you have n degree of freedom, I make it simple. Let's go back to 2R robot. First, we assume that the first motor on the ground is saturated. Okay, we found time, the first floating time. Time is the same space for both motors. So we use this and we come to this and calculate the value of torque here. Again, for the first one on the ground, I assume that this is going to be saturated. So by keeping this saturated, I find the first time interval, floating time. I use this floating time to calculate the torque value of the second. If the torque value of the second one is breaking the limit, this one cannot be saturated. This one must be saturated. So I throw that away, throw the floating time away. I assume this one is saturated and find time. With that time, I come back and calculate the torque value of here. This torque value must be within the limit. It cannot break the limit. But this is the value that this torque must have when it is saturated. So because it was saturated, for example, I go for the second step and assume that this is saturated. I find time interval and I come and calculate this torque value. If at any time this one is breaking the limit, then it means this one must be saturated. I throw that away, I come here, I assume that this is saturated, find the floating time, go and calculate this one. And then with this structure, I'm able to calculate all torques. At least one of them would be saturated and the rest of them within the limit. That would be for n degree of freedom. Everything I explained in this book, Theory of Applied Robotics, one chapter dedicated to time optimal control. I explained everything in detail, proof of those algorithm and convergence theorem, for example. So let's apply the method. For example, here, 2R robot, ideal. Ideal means the arms are massless, and we have two masses. M1 is the mass of the motor in air. M2 is the payload that the gripper is moving. Let's assume that the robot is moving on a straight line from point 1, 1.5 to point -1, 1.5, on a straight horizontal line. Okay, so the path is given rest-to-rest condition. The equations of motion are here, and these coefficients A, B, C, D up to M are expressed here. And as you can see, A, B, C, and others are function of joint variables, means position of the robot. So they are not constant. X or V function that can be applied for phi and theta. What is phi and theta? Let me get back here. Look at this. Theta is the angle of the first arm. Phi, angle of the first arm, theta is absolute value, means position of the first arm respect to the fixed ground. The second one, which is phi, is the position, angular position of the second arm with respect to the first one. So it is a relative position. We can have absolute position for the second one. We get different equation of motion. This is the simplest way. P is the value of torque of the motor on the ground. Q is the value of torque on the air in the first joint or second joint. First joint is on the ground, second joint. Okay. Now, when we apply the method, this is what we get. I assume that 100 and minus 100 is the saturation value. P is, which is here indicated by blue, is the motor on the ground. Here we see that motor on the ground must be saturated all the time. At some point it switches from positive to negative value. And Q means the second motor, it has some value within the limit. Well, we have one switching point for that maneuver, that path of motion. Let's change, before that, show the solution here. See the solution. That's the solution. One more time. That's the minimum time solution. Okay, let's change the maneuver and move the endpoint from 1.90 to 0.5 and 0 on horizontal axis. Okay, let's see what happens. Again, same scenario: 1 meter, 1 meter, 1 kilo, 1 kilo, and 100 Newton meter positive and negative. And this is the solution. Magically, here, as you can see, the number of switching points are multiple. Let me explain. At the beginning of the time, I'm on the left-hand side, motor on the ground, the blue one, is saturated. The other motor is within the limit up to this point. At this time, the motor on the ground, the blue one, doesn't need to be saturated. It cannot be saturated anymore because motor on air is oversaturation, saturated. So that one must be saturated. As you can see at this point, the red one is getting saturated up to that point. Here, the switch, the other motor is saturated. And then another switching here. So switching point can be found. The value of torque value of every motor can be found. And we calculate that at any time which motor is at saturation. That's the solution. And conclusion is that floating time method is a practical method, numerical method to solve time optimal control of multi-degree of freedom. I explained a simple example, but we can add constraint. Means, for example, maximum acceleration of endpoint must be limited. Maximum jerk must be limited. Maximum velocity must be limited, and so on. So number of constraints can make the problem more complicated, but it doesn't matter. This method can handle all of them. Okay, we are done with this interesting problem, at least to me. I hope that you enjoyed that. If you had any question, please email me. I wish you to enjoy the rest of the conference, and I hope we meet each other at Xiamen University of Technology very soon in 2023. Have a good day.